look at the failure criteria for the soil in shear, the original criteria by Moore failure envelope, you can see is a curved surface depicting failure, non-failure cases, as well. If you look at the point B is on the line where the failure occurs. Now, the simplified, the Moore-Coulomb failure criteria is a simple straight line between the shear and direct stresses. So, you can see here is quite easy to simulate as well to predict the stresses, because it is made straight line with an intercept of the shear strength, which is something that we derived earlier. If you look at this equation, is a component of adhesion plus the part of the shear stress as a failure criteria coming from the normal stress. So, basically this gives a linear principle in comparison to the original failure criteria, which is curvilinear. In case of 3-dimensional stresses, it will be a complex surface which will be difficult to derive. So, that is why this simplified Moore-Coulomb criteria is commonly used in most of our foundation design because of its simplicity, and we will be using that in our course throughout the course, which will be very useful. So, one of the parameter what we see here is the undrained shear strength or shear strength you call, and the angle of internal friction. This is a typical C5 soil, which is comprising of sandy clay or clay sand with several fractions. So, basically and the second thing is the effective stress principle. As you know, I think I have shown you some slides with solid particles, voids, and solid particles in contact. I think earlier first 2 classes we were talking about the arrangement of particles in a soil space. So, when you apply the loading, the contact surfaces between solid particles to solid particles is transferring the stresses, and basically the fluid around, suppose if it is a fully saturated soil like marine type of sediments, then it is uniform everywhere. So, they do not take any load and only the loads are transferred by. So, this principle of effective stress was actually originally introduced by Terasaki, and basically it was meant for partly saturated soil as well on the ground conditions, whereas in marine type of soils does not matter, is fully saturated, and also the hydrostatic pressure is same at every point in the soil medium. So, that is why we do not bother whether it is effective stress principle or total stress principle. Total stress is part of the load transfer is via the fluid surrounding, which is anyway later on we are going to remove it, because ultimately we are looking at the behavior of the soil itself. So, that is why throughout this course, though we call it effective stress, we normally use the total stress principle, because we are going to take the buoyant weight of the soil particles itself. So, because it is fully submerged underwater at certain hydrostatic conditions. So, it does not matter whether you are working on effective stress or total stress principle, because the weight of the soil is taken minus the buoyancy. So, if you actually have the particles down there, you take only the effective. So, the symbol, instead of using C dash and sigma dash, phi dash, we will be using for simplicity C, phi and corresponding notation. So, you do not have to worry, we will be working on the total stress principle. What we need to actually look at is the relationship between principal stresses. As you know, if you look at a hydrostatic state of stress, the principal stresses in all direction is same, no. So, what exactly we gather from there? If you apply a state of stress to a particle, whether it is solid or a fluid particle, it is going to experience the internal stresses. So, what we are trying to derive, if you apply sigma 1 and sigma 3 in just 2 dimension, what could be the relationship depending on what type of material, because this will be very often used in the later part of the derivations, whether it is bearing capacity or pile capacity or lateral behavior. So, we just need to know the relationship between sigma 1 and sigma 3. In this particular case, sigma 1 I have just taken as the vertical stress and sigma 3 as horizontal stress. You can actually have vice versa depending on which is more and which is less. For example, if you have lesser sigma 3 and more sigma 1, something is going to happen. Similarly, if you reverse the stress, sigma 3 is larger, the soil is going to get squeezed up down, is not it. So, just now let us look at this. If you look at this, the theta is a natural failure plane, just any angle, it can be any angle depending on type of soil and basically the strength. So, when you look at this picture, when you put it in Morse envelope or Morse diagram. So, you can see sigma 1 is larger and sigma 3 is smaller. Basically sigma 3 is here, and if you look at the triangle in this using a similar triangle principle, you can see here A D and BAD, basically this triangle and this triangle, you can get the properties. One of the important parameter that we are trying to derive is the relationship between the radius of this Morse circle to the distance from this point to this. So, basically is a sin theta, and substitution of. So, what you get is AD is the intercept extended towards the 0 point plus the difference between sigma 1 and sigma 3 divided by 2, basically it is this distance. And when you try to do this sin theta or sin phi, you are trying to get a relationship between sigma 1 and sigma 3. So, very simple triangular principle. So, what we started was using this 90 plus theta, and phi is taken as 45 by phi 2 because sigma 1 is larger, sigma 3 is smaller. And you do this exercise, ultimately we are going to just simplify this. If you just go to this, you can rearrange the terms, you will get something like this. Sigma 1 is a fraction of sigma 3 plus adhesion factor, basically 2 components, and you can actually substitute using mathematical trigonometric functions of 1 minus sin phi by 1. So, you can do that, you will find it in many of the trigonometric identities, or you can derive it and substitute. You are just having a relationship between sigma 1, which is a predominant stress applied vertically, and sigma 3 is a stress applied horizontally. Now, if you go to hydrostatic state of stress, both are equal. So, the coefficient of or the relationship between sigma 1 and sigma 3 is 1, whereas here depending on soil material, whatever the type of soil, if it is a very soft clay, you will go almost very close to fluid. If it is a good material, you will be different. So, that is basically later we will see, it is called coefficient of earth pressure, how much part of the lateral effect is going to be same as the vertical part of the stress. So, in here, if you see here C is coming into picture because we have a generalized C5 soil. If it is a sandy material, this will disappear. If it is a clayey material, then typically you will have a clay type of behavior, or it will become negative. So, this relationship why we derived, basically we will be using this in active or passive earth pressure cases, because remember when we are deriving a foundation capacity, when you apply a loading and to a foundation transfers the loading vertically down, and it puts pressure on the soil and the sides, and that pushes horizontal pressure actively. And what happens to the soil, the state of stress from a the rest case, it is going to get compressed. So, what happens to the soil, and if the soil stresses exceed, the soil will come outside. So, that is basically the idea. Whether you apply vertical stress or the horizontal stress, we need to know the relationship. So, we will just go to 3 cases in this particular earth pressure theory. We will see this picture. If you see at the center, the soil is subjected to vertical and horizontal stresses. Vertical stress is primarily due to, in this case, is due to its own weight, and horizontal stress is due to confinement. Basically, the horizontal stress is a fraction of the vertical stress with certain multiplication factor, and the soil is in equilibrium, it neither moves nor goes back, and that condition is at rest, and at that time the state of stress is such a way that the soil does not move, and not the wall, not the soil. So, it is basically the relationship that we are looking at, which will be quite difficult to find out. Basically, in this condition there are several empirical and some formulas which we will look at it. But when you look at this case, for example, when the wall is weaker, you constructed a wall and try to move towards the left. So, what happens, the soil tries to comes down or go up, depending on whether the wall is moving up or wall is moving this left and right. So, basically the state of stress here, basically the soil is trying to come down and putting pressure downwards, which is going to create active case, that means the soil wedge is moving down. Whereas, in the passive case, we are trying to compress the wall towards the soil, and heaving up basically is a passive case. So, we need to see how we can relate sigma vertical to sigma horizontal or passive I have just denoted as P, so that you can easily. So, this is basically sigma A, this is sigma P, but both times the stress due to its own weight is sigma V. So, in this particular case the soil weight produces the horizontal stress, whereas in this case the ball movement produces primary stress is horizontal, tries to apply the it is against the weight of the soil. So, we just need to derive these three cases. Depending on the situation, we can use this in the foundation design. The first one you can see here, this is what I was trying to explain earlier. The state of stress in the fluid medium like water, you will have the pressure coefficient all around is 1. So, you have a hydrostatic state of stress, whereas if you go to a soil at rest, the vertical pressure is basically the submerged unit weight. All the time we will talk about gamma dash, because the soil is fully submerged in marine conditions. So, depending on the depth at which it is acting, gamma dash times H will give you the pressure at the point of consideration. And K naught for sand, many times people have expressed this, again kind of proposition used many times, 1 minus sin phi. So, if you look at 30 degrees, what will happen to phi? 0.5. So, you will get 50%. So, similarly there was a different proposal like using plasticity index for clay type of soil. This was given by one of the literature. I have just given you for example, which cannot be derived directly, it is only an empirical formula. So, earth pressure at rest, that means the soil is in equilibrium condition, neither moves, and it is in static condition. Basically you see this type of idea, whereas for hydrostatic pressure is very simple and easy to understand, that it is all around uniform. Now, when you go to active earth pressure case, basically the wall move towards outside and the soil is trying to settle down. It could be either due to over surcharge. Sometimes you have like port and harbor structures where you have surcharge, soil is getting compressed. Similar derivation which we just now did it here, exactly the same, I just repeated here. Basically take the triangle from this part as well as from this angle, you try to derive the relationship between sin phi, which is this CD by AC. CD is from the center of the circle to the horizontal. So, this is 90 degree, because it is taken tangent to the circle itself, and then trying to rewrite the values of CD and AC in terms of these triangles, and then substitute here and then rearrange this cot phi, you can rearrange. Ultimately you will get the similar formula what we were deriving. So, the relationship between the sigma 1 was there in the other derivation, is just replaced by sigma A. Sigma 1 was here and sigma 3 was here. So, just rearrange in, that is why you see the negative here, and then you can substitute. I think one of the term is in between, I have just skipped because we have derived here. In this is just skipped because it was arranged from the other side. So, that is why you see a negative sign here, and then replace this with a trigonometric identity. You can just get the formula something like this. So, active earth pressure is a function of your sigma 1, which is gamma times jet, and basically the second and third terms are similar to what we derived. And when in case of C is equal to 0, that means is purely sandy type of material, it will reduce to this relationship between sigma A and sigma B, which is easy to find out because phi will be known to you. And the ratio of sigma active or the horizontal pressure to vertical pressure is called coefficient of earth pressure for active case, that is why we call it Ka. So, as long as you know the value of phi, you will be able to find out the. So, what we are trying to derive is when you apply some sort of stress in the vertical direction, what will be the induced stress on the soil in that vicinity in horizontal direction. That is what we are trying to. It is easy to understand. For example, when you open up a hole in the soil and try to apply the loading due to foundation coming from superstructure, you apply the loading, what happens to the vicinity? The soil is getting squeezed laterally because it is an infinite, semi-infinite soil medium. So, just getting compressed. As long as the compression is not feasible because the soil surrounding is very stiff, what will happen? the soil will not move down, because then settlement will not happen. That means you can classify as a good bearing soil. But if the soil surrounding is actually going to get squeezed away because of porosity, or the soil is not very strong enough, then the soil will just squeeze away and try to settle down. So, two things can happen: either the overburden is too small, so the soil will also come up. We will see this failure cases of foundation later on. When you apply foundation pressure, if the soil on the side is very weak, the soil can get squeezed up also, instead of laterally it can also come up. Once that happens, the foundation will keep on sinking, and that's where the weight of the soil above the foundation layer is very important. If it is heavier and heavier, you are not going to allow the foundation to settle. That means this bearing layer is good. That is why we need to know what will be the pressure put forward by a vertical pressure applied from the foundation and superstructure to the soil in horizontal direction. This relationship is very important, because all along, whether it is a pile foundation design or it is shallow footing design or any type of foundation, this will be very, very important, because that is what the relationship will be using it to derive several formulas for foundation capacity. So, that is why I just was thinking to introduce this. So, basically what you see here is the state of stress in a two dimensional space, horizontal stress, vertical stress, and using a Mohr circle you try to derive the relationship between the property, so called the angle of internal friction, and the intercept, which is basically the cohesive component of the C5 type of soil. And that is what you see here, the distribution of the earth pressure along the depth. Whenever you have the clay type of soil, you will have negative, that's one of the important parameter. If you have a top soil is clay, then you are actually not going to get anything from there. And the angle at which the failure occurs is very important. The soil natural failure by wedging, if you go back to this first picture, when it is trying to fail by deflecting the wall away from the soil, the angle is theta, which is basically 45 plus 5 by 2, whereas when the soil is trying to get squeezed away by the wall towards the soil itself is 45. So, you can see here, you can just imagine it is trying to come down on its own. The failure plane is defined slightly steeper from the horizontal. That means you can easily understand soil is not going to take a very flat failure plane, whereas when you see here, when you are trying to push the soil away, it is taking a slightly reduced angle, which is the soil is trying to heave up towards the land side. So, you can see this is lesser angle for sure, this is bigger angle, because its failure plane is defined by, and the minus or 45 minus 5 by 2, you can easily see that the soil, more soil is trying to go away from the go towards the land. So, that is something that you need to remember. Passive case is 45 minus 5 by 2, active case is 45 plus 5 by 2, the angle will be lesser. Now, imagine if you take a rock or a material is very good, this can actually go into vertical plane, isn't it? If you have a good material, it is not going to take 45 plus 5 by 2, it can even go to 80 degrees failure plane, because you have a stronger strength and it is able to stand in that plane. And if it is water, what will happen? This will become flat. So, that means the failure plane is almost 0. So, that is where you find the difference. The active case, it will take its natural failure plane, whereas the passive case, you are trying to create artificial failure plane depending on the magnitude of deflection. So, it takes the lower angle, pushing more soil towards the land side. So, that is something that I have just described by this, the failure planes occurring in throughout the medium, and just this is a plot of the profile of the pressure calculated, this pressure. Basically, you can plot the Ka coefficients or you can plot the pressure. Similarly, we could derive exactly same procedure, only thing is in this case horizontal stress is higher. So, passive earth pressure or the soil, the pressure applied on the soil by the movement of the wall is more. So, sigma p comes larger and sigma v becomes smaller. So, that is why the soil is able to move. Imagine if you go to this picture, I just go back again, if you have sufficient amount of vertical stress at the top. For example, you put so many concrete blocks, what will happen? The soil will not be able to heave upwards. So that is why in this case we are making the effort required to move the wall is more than the weight of the soil, which is basically from this point to this point applied there. Then only the soil will move. Suppose if the sigma v is larger, for sure the wall is not going to be able to move towards the soil. That is the condition that we are looking at. So that is why in the Mohr circle you see the sigma p is larger, sigma b is smaller. So basically that is the idea behind the passive, and you just do exactly the similar triangular principles and try to find out the relationship between the phi and the other variables and substitute. What you are going to get is similar expression, except that you are going to see plus here because it is changed the other way around. So you can also substitute similar, and the relationship you see here, the passive earth pressure is the vertical component plus the cohesive component, which is similar picture you can see in the diagram. This failure plane is 45 minus pi by 2 because it is shallow, and you can get the distribution of the passive earth pressure along the depth. So this relationship will also guide us in several cases. See, for example, when I apply foundation pressure, below the foundation the soil is getting vertical stress and getting horizontal stress due to this, and then on the side of the foundation the primary stress is horizontal, trying to squeeze the soil upwards. If we draw one picture, for example, so you take a cut foundation, something like this. If I apply, you take one soil element here, the predominant stress applied here is the vertical pressure, which is sigma v, and sigma h. For this foundation to be in equilibrium, whatever the sigma h applied should be able to satisfy the equation for sigma v, so that it will not move down. So in order for the sigma h to be there, if you take a soil sample here, this soil sample the soil element should be in equilibrium. Otherwise, if this gives away, for example, if this height is not sufficient enough, the soil will get squeezed away because this is a free area, whereas it cannot go this way because the soil is continuously infinite. So that is where we will be requiring the passive case here, where the applied stress is horizontal, which we are going to relate. That is why you need to know this both active and passive cases will be used in derivation of foundation capacity. So when you look at load transfer, so that we can easily derive some bearing capacities of footings or pile foundations. So if you look at the reason why we were trying to go for pile foundation in many cases of large load or soil is not good. So you see this particular case, predominantly the footing type of soil, footing type of foundation, the soil is getting vertical pressure just immediately beneath the foundation, but then it distributes in a manner depending on the type of soil. If it is a sandy soil, it takes certain path. If it is a clay type of soil, it takes different load distribution, or if it is a rocky material, directly it is taken by bearing. So you can see here, if it is a C5 soil with sand and clay, you will see that a mixed pattern of the soil pressure distribution will take place. Whereas in the case of pile foundation, predominantly we are trying to fail the soil by shear along the surface between the soil and the foundation material. And of course, when it is being done, what is happening is the soil on the side is getting squeezed away because the pile is getting inserted. So whatever the friction that it has to overcome during the same period or during the same time, the soil is actually getting lateral pressure, and which needs to be taken into account when we are doing the foundation capacity. I think with this we will stop, so that we can go into foundation types. Probably we will start with the shallow footing with some derivations to understand how we can relate the bearing capacity to parent parameters. So, what we will do is we will just quickly derive, because if you derive this relationship between the bearing capacity and the parent parameters for phi soil, C phi soil or C soil, then we use the same principle to extend the bearing capacity for pile foundations. Before that, we will just quickly understand what is the failure modes. As I was just explaining here, predominantly the type of failure for various types of soil is very difficult to predict, and that is why you will see that certain uncertainties arise, because it is not a uniform material. I think the first class itself I was trying to talk about, when you have a hypothesis of a failure pattern. For example, you take a steel material, when you explain failure by tensile means by necking and then breaking, it is going to happen for most of the steels. 99% of the steel material will behave similar manner, whereas in soil conditions, depending on the soil at the particular to the foundation location in the vicinity and type of soil, the failure pattern is going to be different. So, what the researchers have done, they have just proposed several types of failure, and then finding out the solution for each one of the case, and then they have adapted the least one for some cases, they have adapted mean cases for sometimes, and that is why you will see that empirical coefficients play a major role, combining some of them. You take combination of some of the failure patterns. That is why we need to understand what is the mode of failure, and then based on that we can find out the foundation capacity. So, what we define is ultimate bearing capacity is the least pressure by which the foundation will fail by shear. So, basically what we are looking at here, if you put the pressure here at this point, when you apply that pressure, the foundation will just fail by, or it will make the soil to fail by shear, and that will be the pressure that we are looking at, called ultimate bearing capacity. So, that means we are going into ultimate strength principles, rather than when you are looking at the previous semester we were talking about design of steel structures, we were looking at allowable stress method, we take the fraction of yield as the allowable strength. In this particular case, we want to look at the ultimate strength, then later on we apply a factor safety to arrive at the allowable bearing capacity, which we will compare with the working stress principles. In many cases, this will be quite useful, because that is the maximum that the soil can take, and that is what we are trying to derive at it. So, if you look at these pictures, the first and the second and the third, I think we can spend some time on this. So, if you apply a bearing pressure from the superstructure and foundation, and the soil beneath is getting stressed in a similar way what we were deriving just now, basically the active pressure case, soil is getting compressed, it is exerting lateral pressure on the soil beneath on the sides, and because it does not have sufficient strength, the soil is heaving away, and that means the foundation is going to settle, and at certain point it will find an equilibrium and then will stop, and that is the point that we are interested to find out. When it stops, how much is the settlement, how much is the bearing capacity. Several people have worked from 1940s, starting with Teresahi, Meyerhoff and several other researchers, come up with different ideas. We will see all three of them, so that we could understand what exactly is going on. So, the general failure is basically a pattern which has got soil displacement laterally, soil heaving up vertically. So, by doing this, what has happened is some amount of overburden is created at the top, because the soil is going up. Now, you go to the extreme case in this last one. Imagine this is what will happen when you have very soft clay. For example, the other day I was talking about, if you go into a marshy area, you step on it, what will happen? You will simply go down vertically without any resistance, and that is what will happen if the material is too soft or too loose, even if it is sand, for example. Now, this is the intermediate case, shear combined with some amount of general failure. So, basically local shear. This is purely a punching shear, very similar to what you normally study with the concrete punching shear, just vertical cut. This is what will happen if you step onto water, isn't it? Straight away go down. Now, you compare on the right hand side, there are three diagrams given to you to understand what exactly happened for a given pressure, for example, you take a particular pressure, you come to A, it has got lesser settlement, which is this, and if you take the same pressure to C, you see that settlement is larger. So, you can easily understand, depending on the type of basically the material, for a given pressure ABC you will have a larger settlement, or for a given limiting settlement, that is what we will be working out when you are designing a foundation. We will be limiting the foundation settlement to say 25 mm for particular structure. So, you take a particular settlement case and then just go around. This gives you the lower bearing pressure, which is basically easy to understand, the last one, because of the local failure. But if you go to the A, which is a more general failure, you can take a large bearing capacity, because its movement is restricted by soil in the beneath and the surrounding areas. So, any one of them can happen depending on what type of soil, but we can easily see this will happen definitely on a very soft material, whereas this will be a good soil with good bearing stratum. So, that is something that we can derive. So, what we will do is we will just quickly look at what we need to do is, when I was talking about soil in equilibrium, there are two cases, basically an upper bound and a lower bound. Upper bound, true failure load will be larger than corresponding to equilibrium. Lower bound is, you will find the load will be higher than the equilibrium case. The upper bound will be a mechanism case. I think you might have studied in your applied mechanics, the mechanism by which the load, the true failure load will be smaller, corresponding to a mechanism, basically formation of hinges. So, we will see both of the cases. For simple type of soil, basically we will see the C equal to 0, that means a pure sandy material, and clay type of soil to understand. But then when we go to a comprehensive C5 soil, the derivation may become little bit bigger. We try to derive, but finally I will give you the equations which could be used for. So, in this basic idea is, you may have several solutions. We already have got 3 types of failure modes, and if you look at the shape of this, several researchers have proposed different angle, different shapes to these wedges of active and passive soil triangles, and basically can apply this one to pure sand, pure clay, or C5 soil. So, you will have several solutions. So, the idea of the perfectly plastic stress strain principle is, so we do not have a tensile capacity for sand. So, when you have a contact stresses, once it is dislocated, it cannot be brought back. So, that is one of the biggest worry in soil behavior. Once you disturb and dislocate, for example, you have a foundation, once it is the bond is broken, for example, on this place, it cannot be brought back, because it is permanently settled, which you cannot bring it back unless is like other types of steel material or other structural materials, where as long as if it is within the elastic limit, once the load is removed, it will come back. Whereas, in this case, once you break the bond, or once you make this strain to happen on the soil, even if you remove the load afterwards, what will happen? It will never be able to come back, because it is not structural bonding is there. That is one of the problem. That is why we need to be very careful. When we reach this capacity, it is not good. So, we need to be finding a factor of safety on this strays, the shear stress or shear strain. Basically, somewhere here we should stop, so that it does not permanently break, and basically that is the easiest way of adapting the foundation failure. So, we just, I think it is a similar picture what we were seeing for the active case, sigma 1 and sigma 3, which is basically a small soil element, same Mohr circle is drawn there. I think is repeated from what we have just re-summarized, because I used to take this one in the end. So, in any case, you do not need to read again. Now, you look at this picture, we will just look at one of the lower bound solution today. When you apply, P is the foundation load coming from superstructure over a area of say foundation width of B. We just now consider this as a strip footing that is continuous for a longer distance. So, only a 2-dimensional effect will be there. Later we will see the 3-dimensional effect if the foundation width is or length is smaller. So, when you apply, the pressure will be the load divided by B multiplied by 1 unit width or unit length, I would say. So, you have a pressure applied is Q, and soil beneath here is applied by the vertical stress which is in yellow color, and horizontal stress which is generated due to the active earth pressure case. So, which we denote as sigma 3. So, this sigma 3 must be equal to the stress at the element on the side. So, that these two soil elements 1 and 2 are not moving, they will be in equilibrium. If the soil element 2 starts to move because the soil pressure on the side is, or the vertical pressure is on the side is not enough, soil will heave up, because the produced sigma 3 will be higher than what you actually gain from sigma naught. So, that is the equilibrium. So, the whole thing is very simple idea. Apply a pressure here, this soil element generates the active case and transfer to the side element as a passive case, and basically is sustained by the overburden pressure. We call it overburden. Basically, this is the soil that keeps these two elements in equilibrium condition. Imagine if that is not the case, we can always go and put some weight there, isn't it? The larger the weight you put on the sides, the more the pressure that you can apply to the foundation itself. So, that is the idea. So, you can see here now very important matter is the active and passive earth pressure cases here, and the overburden pressure, the weight of the soil on the side is going to be very important. As long as you can understand this principle, this is the principle that will be adopted almost throughout the foundation design case. That means the evaluation of overburden pressure is an important activity in the whole process of estimation of foundation capacity. So, how do we derive this relationship? That is what we will spending a lot of time this morning. Basically, this is sigma V and sigma A you try to find out, and then take that sigma A, apply to this side element as sigma P and try to find out sigma V. And once you equate this to this, that is the point of equilibrium, and basically very simple idea. We can find out, we can come reverse way, to find out what should be the Q value at which equilibrium exists, and that is what we are interested, that we call it ultimate bearing capacity or bearing strength. I have just summarized all of them, you could easily go through. The principle behind is equating two soil elements, one beneath, one on the side. By doing this all of them, what you see here Q u I am getting, because this I have taken as pure clay type of soil. You see on the left side phi is equal to 0, I assume it is a pure clay for a simplified case, because when you go for other cases you will find little bit difficult just to understand. So, when I do all these substitutions, I get Q ultimate is 4 times the shear strength of the soil at that layer, and when foundation D is 0, basically I think this depth, that means this is brought to the surface level, because when you make this foundation to the surface level, the overburden pressure is gamma is there, but D is 0. So, you have, so that is the case that you get this, otherwise the ultimate bearing capacity will be 4 times shear strength plus whatever the surcharge pressure you have. So, the deeper that you go, you get a better situation, isn't it? That is very easy to understand, and when you bring to the surface, you get your limiting value is 4 times the shear strength. Now, imagine most of the shallow footings in building construction, you just go and make a cut and do it, whereas in the jacket case, when we have a mud mat, I think I have explained what is mud mat now last time. It is a temporary foundation required for stabilizing the jacket on the seabed, which will be kept on the surface. So, this will be the case where we will not bury the jacket underground, we will be placing it on the surface. So, that this will be the case that we will be looking at. So, what we need is, what is this factor? Factor 4, we call it bearing capacity factor. Later on, these various researchers came with different values. This is only a simplified derivation, and you will find in literatures different values, slightly bigger than what is derived for this so called lower bound solution.